In 1827, English botanist Robert Brown was looking at pollen floating on water, and he noticed that it was doing something rather strange, something that he couldn't explain. It was named Brownian motion after him. Well, this same phenomenon can be observed by looking at smoke under a microscope. And that's what we have here. We have a smoke cell where I can trap some smoke and I can look at it through a microscope. So first I create some smoke by using this. Then the smoke I place in here. When I look at it like this. Come have a look. And there we have it. You see those little tiny dots? Well, they are particles of smoke. And if you look at them closely, you can see that they're moving around in quite an unusual way. The particles are swarming and gibbering around on the spot. Now this was proof, if proof were needed, that gas, like the air we breathe, is made out of millions of tiny invisible particles. Now those smoke particles were having collisions with unseen smaller air molecules, oxygen and nitrogen. And so through this experiment we have direct experimental evidence that gases are made out of particles in the same way that solids and liquids are. But there are some differences. In this model of a solid, you can see the atoms are vibrating with very, very small amounts of movement. This represents a cold, solid object. But we can turn the energy up. And even though it be a solid, look how this black square gets pushed above, ever so slightly. But though it remains a solid, it has now started to occupy a slightly larger space. This is because the atoms vibrating are pushing each other apart ever so slightly. This is a thermal expansion. Now I can demonstrate the thermal expansion of a solid quite easily. I have here a big strong piece of metal and a smaller, slightly less strong piece of metal on this side. And what I'm going to do is I'm going to heat up this piece of metal until it expands slightly, till all of the atoms are ringing off each other, just giving each other a little bit more space, which of course will extend the length of the bar. I will tighten it and tighten it. And then I'm going to do something quite dramatic. As it gets warm, I will tighten this bolt. So you can see that the expansion was such that when it rapidly cooled down, it had the power to break this metal bar simply because the atoms were contracting into their rightful places once more. But can a liquid expand when it is hot? Well, here is a liquid. You can see the particles are moving. If I make the liquid warmer, you can see that it's pushing the black square up. There's more energy, the atoms are moving more, and therefore taking up more space. Now this is exactly what happens inside a thermometer. When the thermometer is in contact with something with lots of thermal energy, and the particles are vibrating more, then it causes the mercury atoms in here to vibrate more, so they take up more space like this here. Taking up more space means they creep up the scale, and this is how we measure temperature with a thermometer. So does a gas expand when its thermal energy increases? Well, I have a balloon in this freezer, and I've sellotaped a piece of string around the balloon. What I'm going to do is I'm going to mark on the piece of string exactly one circumference. I'm going to allow it to get warm, and then I'm going to then show you it again to see has the volume of the balloon increased, has the circumference of the balloon extended. So here we go. Here is the balloon, and I'm going to very quickly put the string around on the black line that I've already marked. I'm going to mark on the string just there the circumference. I'm now going to put this in a safe place and allow it to warm up, and then we shall come back to it in 2 minutes to see what the circumference of the balloon is once this gas has reached thermal equilibrium with the gas in this room. Now a minute or two has elapsed. I'm going to wrap the string back around to see whether or not the gas inside has expanded, and look at that. The black mark is now 2 to 3 centimeters into the circumference. That the actual circumference has increased by about 2 to 3 centimeters. The gas inside, having gained more thermal energy, has expanded. So there we have a representation of the gas. The volume is the space in which the gas is occupying. When I turn the energy up, the volume that the gas occupies has grown. Thermal expansion has caused the gas to occupy a larger volume. It was only when that link was made between Brownian motion and the way in which a gas behaves that scientists made any progress in predicting what would happen if they changed the state of a gas. By imagining that a gas was made up of thousands of tiny little particles, they could understand exactly why allowing it to warm up and gain thermal energy would cause it to expand. They understood the mechanism by which that could happen, and this gave the scientists enough confidence to believe that the particle model for a gas is correct.